if that's okay, to pronounce is to introduce Florian Siepe. And Florian,
right now we are 2 minutes behind.
Okay, well that's better than I expected. Actually, you did a fantastic job in catching us up.
We skipped the slide break.
Okay, you did a fantastic job. Thank you. Florian is a software engineer at Viessmann IT service, and after finishing his bachelor's degree in 2021, he's currently pursuing his master studies at the University of Marburg in Germany. It's interesting, out of all of the speakers, he's the young man, but he has an old soul. He's the fun fact about that we have for Florian is that a few years ago he started listening to good old rock and roll, and now he can't listen to current stuff anymore. He has to listen to music that actually is much more probably aligned with my timeline. So Florian, with that, may I introduce you, sir, and thank you very much for joining us today. I look forward to hearing what you've got to say.
Thank you, Roger, for the quite gentle introduction. And as we're late on time, I'd like to, so let's just dive into my slide deck. So we're dealing today about bills of materials. That's basically just comes from a manufacturing point of view, and there every product can be composed out of different other sub-products. And here we will explore how to resolve them and use them in an e-commerce site. So, but first, let's have a quick look on the agenda. First, I'd like to present the who's me, and why am I standing here. After that, we'll just dive a bit into the use case. I will show you some demo about the e-commerce site we're developing. And right after that, we'll developing a PGQL query step by step together. So I'll help you get in touch with running PGQL as a query language in your own applications in the future. At the end, we might have a short Q&A to answer all of your questions. So, who am I? Roger already said it. I'm currently at my master's studies in the University of Marburg, and I'm working for Viessmann quite a few years now. There I'm primarily responsible with about developing front end, the e-commerce site itself, and also a bit of backend development. Viessmann itself is a German-based company, and we're producing heating and cooling systems for both private and business use case. And we have grown in the last few decades a bit, so we have currently around 30,000 employees in dozens of countries. So, yeah. So let's dive into the use case, and there we see a screenshot of our e-commerce shop. This is a B2B e-commerce shop, so we'll have to mention a few details which are quite relevant in this business area. In a B2B e-commerce shop, you have to explain to your customer what are your products about. The end user is not pursuing or experiencing shopping experience itself. However, he has to he wants to explore your products, your connections between the products, what products, maybe some spare parts for it. And there we have a much more technical view. And to be able to solve this, we want to let the users explore our product catalog and to navigate through a whole product tree. So let's quickly have a few demo out of it. So we're currently seeing a product details page we've shown in the screenshot before, and in this middle section here we have a thing which is called a part list or a bill of materials, and this tells me as an end user this our product, which has this number, is composed out of 7 other products. For example, there is a boiler or there's a burner built into it. And each of these parts you're seeing here has itself the additional subparts. And therefore we want to be able for the user to search, for example, in it. So let's say I'm an end user and want to search in this whole product tree. And for example, I'm searching for a burner. Of course, I have to type it the right way. Okay, great. And in the search results section, I get my subpart as well as the path I need to take into consideration when I want to navigate through the tree. So I can see here that, for example, this matrix burner is part of a castle, which is part of our main product here, and there we have this whole path we're running into. Yeah, great. So let's get back to the slides a bit after we've seen a bit of the e-commerce shop, and let's dive a bit into more of the technical details. In our company, SAP as an ERP system is our single source of truth. That's the place where all the data lies and all the data comes from. And with having said that, there's a lot of legacy code, legacy data, which need to be extracted and to be normalized to be able to use it in an e-commerce size. For this, we have application running, which is called the feeder here, which extracts all of this product data out of SAP and pulls it into Elasticsearch for the search part, as well as an Oracle database for to be able to read this data into the graph server later. With having the graph in memory, we have another application which will then connect to the Oracle graph server itself, as well as the Elasticsearch, to be able to perform all of these searches within a part list. So let's dive a bit into the Oracle database schema we have running. The most important tables we have are on the bottom. As you have seen here, we have just one entity, which is a material or a product, which itself is identified by a material number and has some additional properties to it, like spare part, or is it a wear part, or whatever. And all of these materials are connected to edges, which are specified in our part of relationship. And this is quite a simple graph model. However, as a larger company, we're distributing our products in quite a few countries, and every country has itself an own unique product catalog. There are some overlaps, of course, into it. However, they are separately distinct by each other. And to be able to resolve this out of these two base tables we have here, we are creating some views where we identify our country we are currently doing the product catalog, as well as the language which is associated to this catalog. And from these for these views, you can see an example here on the right bottom. We're reading the data into memory into PGX, or the graph server. And with having read this into memory, it may have some sample structure like you can see here. There we have the same material we've seen before on the website. This is called the CU3A038, and there are all the same 7 sub-materials which are directly connected to the space product. So then let's directly dive into the query part, and there we go to the PGX web console we've seen before. So let's first start with having some base query where we fetch our or where we can explore our graph model. I've already run this here, so you can see we have some material, we have some properties on it, we have a material number, and as well as the connections to other products. However, if you can remember the short demo I've shown before, we want to be able to resolve this bill of materials in a much deeper way. We don't only want to have the first level. We want to have additional levels of this product itself. So we have to adapt our query here a bit further. So first, we may want to limit our search result to a specific product. And there you can see it's the same material number you've seen before. And if we run this query, we get basically the same result as on the slides. Great. So maybe we want to dive a bit more further into it. So let's then start by having a look programmatically or by a query language how many direct submaterials are attached to this CU3A. By doing that, we adapt the query with this count function, with this built-in count function, which allows us to directly see the direct amount of products which are attached to it. Great. As you've seen here, we are currently dealing with the first level only. And we could have done this with a relational database itself. We don't have to use graphs for it. We could use quite a simple join from two tables, and it would be sufficient for this use case. However, we want to have this recursive approach in it. And to do so, we are expanding the match clause we see here a bit further. I'll just paste it in here and quite shortly explain to you what we're doing here. In this match clause, we don't only have this direct relationship we've seen before. Now we have a nested sub clause matched into it. And you may see this star here. It's also called the clean star. And this specifies how many or how often this pattern in the inner clause can be repeated. And the star itself says it can be repeated from 0 to an unlimited number. And if we run this, we get now a quite large table with all subparts and the subparts which have a path between this base product of CU3A and its nested subparts. Great. Here you can imagine that if we have a base product which is quite high in the product hierarchy as our starting point, we are resolving the full catalog. This is not very useful for us as we have a lot of data then. So let's start by limiting our query depth. And for this, we exchange the clean star to have some kind of fixed cardinalities. And here I say I want to have at least, or the path has to have a length of at least 1 step, but at maximum 10 steps. And if we run this, let's use 3 for the sake of the demo. And there we have quite less items in here. As a last step, we want to add to return the whole path we've taken from our base product into the subpart itself. So for this, we're using another function, which is called the array aggregate. This basically can aggregate our reference of E, or reference of V1, which is in this nested subquery, and we're getting the material number of it and writing it as an array into the final result. And if we execute this, we have now our material path built in. And if we take a look at it, we're getting from our base product through, for example, now this product and this product right into our direct subpart, which is here. And as you remember, this is quite the same as we see here in the web UI. And with having this end result, we are now able to explain to our customer, how is this product composed and how is this subpart located within the context of our base product. Great. So let's have quite a short recap about what we've done. We've seen that PGQL itself is quite a powerful query language to handle graph data and as well as handling recursive data with an unlimited number of hops. We've seen that we have a web UI of PGX to incrementally develop your and directly get feedback whether your query works or whether it does not work. What I have not shown here is that Oracle Graph Server itself offers a Java API, which allows you to connect to PGX programmatically, run your queries, return it, and do many, many more advanced things the other speakers have talked about. As a further idea, which Melly already expanded a bit further, is that graphs are quite suitable for implementing recommendation systems. Melly has shown it with her movie dataset. However, this could be a use case for our e-commerce site here as well. So this is maybe a further step. We will have a quick look into it. Great. And if we still have time, we are quite ready for a Q&A or some questions.
We do have some time, Florian, and thank you for to all you and all the speakers for helping us catch up. I think we're doing well on time now. I believe our next scheduled session is at 1:05. So we have some time for some discussion, and we can also maybe have a very short break. So I had a question around, I got a couple of questions, if I may. You showed the interesting recursive query where you had the star to show multiple hops going down that query. How deep do you expect it to be? I was just curious about how deep you expect to go.
Oh, we can all try this out. So let's run this query again and get to the last result set. From this base product, we currently only have 4 hops. So this array length of 3 plus the last one. However, for other materials which are different, this could be less and this could be more. But usually with 3 or 5 hops, you're set.
Okay, all right. And that's the nice thing is you don't have to specify. You have specified. It's not one number. It can be a variable path. You can say 1 to 10 or 1
exactly.
to 3, or you can have the star, and kind of the graph query language gives you the ability to do that. So what do users do with your system? Like how, from a business point of view, when they run this query and when they see all the different subparts returned, what would be the next action? So
we can try this out. We're now running as a user on our end or on our e-commerce site. From this part list, the user is, for example, directly to add this part into his shopping cart, and additionally, we've seen this path before, and now we are able to use this path to navigate through the whole product tree. For example, I now just routed to the boiler part, which is within this part list. And with this set, users can quite interactively navigate through all this product tree and explore the catalog.
Right. And it's like intuitive navigation based on what are the components that create this.
Exactly. It's about making the user experience better and let the users to find his desired results in a faster way.
Right. And yeah, that makes a lot of sense. So Roger, do you have any questions? I don't see any other questions in the Q&A.
No, I think it was good to see a practical, real world use case being presented. So, but thank you very much. It was good.
Right. So with that, I'm going to switch over to our Slack workspace again.